see how we calculate a doubly reinforced beam, reinforced concrete beam. So we have this beam 5 meter span. First we need the loads. And we have two types of loads, the permanent load and the variable loads. I'll show how to get these loads, for example, from a slab. Let's go start here. We have this slab 5 meters by 8 meters and it has 3 beams. One on this corner, another on this corner, one on the middle. I could calculate this beam here on the corner, but there's little to calculate from there. It's better the one on the middle, since he is gonna have loads from one side and the other side transmitting to the beam. So on this span, from this beam to this beam, we have 4 meters. From here to here, 4 meters. Looking in the cross section, to be like this: a beam here, another beam here, and they are simply supported. And the slab on top. For the slab, let's adopt this height, 0.261 meters. Let's adopt for variable load 5 kilonewtons per square meters on top of the slab, and for a finish or walls, let's adopt 8 kilonewtons per square meters. I get this from, for example, walls. I know from hollow brick walls with plastering from, for example, 26 centimeters. This is the weight and this is the height. It could be 2.7, then so let's consider 7.8. This is hollow bricks, they are not solid, so 7.8 we can consider like 8. It came from there, kilograms per square meter. And since we are calculating for this beam on the middle, it gets loads from half of the span from here and half from the span from here. So it's 4 meters here, 4 meters here, as we saw. 4 here, it comes here. And this cross section of the beam, so half of 4 is 2 meters. From this other span, half 4 divided by 2, it's 2 meters. So this is how we're gonna get the loads, the permanent loads and variable loads from the forces that we are considering on top of this slab. For the dead load of the slab, it's basically, so the 2 meters from this side, 2 meters of this, 4 multiplied by the, since it's a dead load and it's reinforced concrete, we are considering for this slab, it will be 0 multiplied by the height of the slab, 0.261 multiplied by 25, that is the density of reinforced concrete, that gives us 26.1 kilonewtons per meter. Okay, for the finishes and walls, it's basically the half of this side of the slab and the half of this side, that is 2 plus 2 multiplied by the load of the wall that we are considering, what they gave us, 32 kilonewtons per meter. Okay, the variable load, it's simply the 5 multiplied by half of the what we are considering of the span on this side and half of the span we are considering this side. So it's 2 plus 2, 4 multiplied by 5. This is why we have 20 kilonewtons per meter. Okay, so we transfer these loads. This is a dead load and this is a permanent load too. So the two together, they are 58.1. They are permanent loads and the other one is 20. So we transfer these loads to the beam The beam has 5 meters long, is this, and is supported on brick walls, so we simply support it 5 meters. So 5 meters here. This will be the cross section of the beam. 5 meters the load, so we have the 58.10, that is the two permanent loads together, plus the variable load 20, and for the self weight we are going to determine this load on the following way. Since it's a simply supported beam, the effective depth will be calculated according with the Eurocode is L over 14, for example, because from this table it's since it's a beam, it will be highly stressed concrete and not lightly stressed concrete. It's highly stressed and simply supported beam. From the Eurocode it comes that it's L over D, it is equal to 14. So we can simply pass to the other side and divide it. The 5 meter span divided by 14 would give us 0.357 meters. Let's consider 450 millimeter. It could be 400. We could measure to 400. Let's calculate it with 450. And for the base of this cross section of the beam, let's adopt so it will be D divided by 2, so 450 divided by 2 give 225. Let's use 250. This is how we got the estimation for this section. Okay, so the total depth will be simply, if we look as this, it will be the effective depth plus nominal cover plus diameter of the links, stirrups, plus half of the diameter of the main rebar on the bottom. Okay, give us, we are adopting here 560. I'll tell how I got this nominal cover. It was I got it from the Eurocode. So I adopted the XC4 from Eurocodes for exposure classes, and this basically means this means XC4 cyclically wet and dry concrete surface subject to water contact. Okay, so since we know is this one that we are after, XC4 could be another one depending of the situation you have in your location. So if we go here to the table that is in the Eurocode, XC4, and it will cross with the X4, 30 millimeters for minimum cover. Okay, and we know the nominal cover will be equal to this expression, the minimum cover plus a deviation factor. So this minimum cover first has to be calculated by this equation from the Eurocode, and basically all this is nothing more. There are a lot of specifications, but going forward it will be the minimal cover we got from here. For example, I'm thinking to adopt here for main rebars 32, and for stirrups this time I want to use less stirrups, diameter smaller than the last time, because there was a big spacing for the links in the end, so we could have reduced it. This time I'm just going to 6 or 8, we can reduce it. That's very important, different from the other time. Here we can save a lot of steel. I'm going for, I could put 6 millimeters for diameter of stirrups. I'm going for 8 and 32. So for the main rebar. So basically here it will go 32 of the rebar. It will be the maximum, the 32, or the 30. That was the one we saw on this table from XC4, S4, 30. And there are a lot of factors here that we don't need it, and of 10 millimeters, but we could put 20. I advise to have 20 there. So this, what is the maximum of these values is the 32. That is the diameter of the rebar we are adopting. So it's equal to 32. The links are 8, the main rebar is 32, so it's logically this cover should be minimum 32 plus a deviation factor of 10 millimeters. In the calculation of the nominal cover, we can consider 10 millimeters of deviation. So it's what gives us for nominal cover 32 of the rebar plus a margin of 10 millimeters that give us 42 millimeters for the nominal cover. So this is how you get from Eurocode in nominal cover, 42. Usually this will give good results. Okay, having this, the D prime will be simply the 42 plus diameter of stirrups. And I'm thinking on the top is simply, since it will be a simple doubly reinforced concrete beam, I'm thinking maybe I will use 20. So it's 20 divided by 2, the D prime, that gives 60 millimeters. Okay. So we have here all factors. Let's define for concrete C30 megapascal, for rebars S500. The FYD, it's simply 500 divided by safety factor of steel 1.15. Okay, we have everything. Since we have the nominal cover, this is how we got the total depth, that we are estimating 516 and 215 for wide. So the self-weight is simply the total depth multiplied by B, 250, multiplied by the reinforced concrete density 25, will give us 3.23 kilonewtons per meter, since it's a beam, not a slab. When it's a slab, we are considering per square meter, but since it's a beam, let's go for kilonewtons per meter. So we have everything that we need, the loads, the dimension of the cross section for the beam. Let's start calculating. We need to start calculating at the ultimate limit state, and factoring these loads will be 1.35 multiplied by the permanent load plus 1.5 multiplied by the variable load, and this is basically the UDL, that is the factory loads. So it will be 1.35 multiplied by 3.23, that is a permanent load, plus the other load 58.10, 58.10, plus 1.5 multiplied by 20, what gives us 112 kilonewtons per meter. Okay, according to the Eurocode, we have this at the ultimate limit state. After this, we have to calculate two things to get the rebars, the reinforcement. It's go for the bending moments, and later on for the shear. For the bending moments, it's a simply supported beam. It will be the factory load multiplied by the span, it is 5 meters elevated by 2 over 8. Will give us, it's 112.79 multiplied by 5 elevated by 2 over 8, give us 352 kilonewtons per meter. Okay, so the main reinforcement, how are we gonna calculate here? So the reinforcement, we know it's a double reinforcement we are calculating, but just we know in advance, but just when we are calculating we can get this conclusion. So we have from the Eurocode K equal to the factor moment divided by B multiplied by D elevated by 2 multiplied by FCK. And when we take this moment, 352.47 that we calculated, divided by B, it's 250, multiplied by the effective depth, that is 415, elevated by 2, multiplied by the FCK of the concrete that we are using, 30. All this gives us a K of 0.232. So here in this K we can see why I used the effective depth 450 and not 400. That was closer to what we calculated. Because if we put here, look into this K, 0.232. If we put there 400 millimeters for the effective depth, it changed drastically and it goes to 0.293. It is much more steel to spend, much more. So I keep it here 450. It seems to be the perfect high to get a good equilibrium, that we get 0.232, and this value is bigger than the K limit that is stated as 0.167, so it's a doubly reinforced beam. This is how we get to the conclusion. And now we know it's a doubly reinforced. It will have longitudinal bars on the top and on the bottom. And for that we can get from this equation another information, that is the D prime divided by D. D prime 60 divided by D 450 gives us 0.133. And we know that if it's less than 0.171, that is a fixed value there, it will yield the steel, so it's safe. We can continue. If it didn't yield, we have to recalculate the dimensions, so we get the result. It has to be smaller than 0.171. Okay, so going forward, now to calculate the rebars, we start by calculating the rebars on top of the beam, here on top, and that will be given by this equation. This is the K less the K limit, that is the 0.167, the FCK multiplied by FCK, that is 30 of the concrete we are using, multiplied by B, that is 250, multiplied by D, that is 450, over 0.87 FYK of the steel, that is 500, multiplied by D, it is 550, less the D prime, that is 60 millimeters. Okay, so this K less this K limit is basically this one less this one, will give us for the top, so it's basically like a percentage of the steel. It gives us 0.065 to use on the top. So from here we can simply go to the equation and replace all the values. Since we have this k, 0.065 multiplied by FCK, that is 30, multiplied by B, 250, multiplied by D, that is 450, elevated by 2, over 0.87, FYK, that is the S500, still we are using, less D, again, that is 450, less 60 millimeters. This gives us 581 square millimeters for rebars on the top. When we get this, we have to later on to check the minimal and the maximum steel that we can use, and it's given by this equation, this expression. Of course, in the Eurocode it's all dispersed, this information. Here I have it compact. It should be the maximum between this part, 0.26 FCTM multiplied by V multiplied by D over FYK, and whatever is the maximum, and 0.0013 multiplied by B multiplied by D. Replacing all these values, we get what is the area of section of steel that we need for the minimum area, and it ends up to be 169 square millimeters between these two. Okay, so and the maximum, so the steel is limited by the maximum that is given by 0.04 multiplied by the section, the cross section of the beam, the reinforced concrete beam, that is basically 250 multiplied by 450. So it will give us 5,160 square millimeters. Of course, this I don't think will ever happen, but this is the limit of steel we could use. So here on the minimum we could use two bars on top of 12, give us 226, that is bigger than this. Okay, if we went to 10, it will be less than what we need for minimum, for the minimum. So for minimum we will need this one. Okay, so we can see that on the top we have 581. It's more than the minimum. So we could start by saying let's use 2 bars on the top of diameter of 20, would give us 628 square millimeters. Bigger than this, we are okay. Even when we estimate here on the beginning, we were thinking on the D prime to use the 20 rebars on the top, and it seems it's okay. If we try to use it 16, 402, it's not enough, so should use the diameter of 20. Okay, now for the bottom reinforcement here. For the bottom reinforcement, it's basically the limit of when we are calculating the limit for a simply supported beam, that is the K limit, that is 0.167, that is what is missing. Multiply by FCK, multiply by V, multiply by D, divided by 2 over the same expression than before, 0.87 FYK, multiplied by the lever arm limit. This lever arm limit for a doubly reinforced concrete is different than before. Is given by this expression. That basically when we replace all the values for this limit, it will give us 0.82 of the effective depth. And before we have the limit that was 0.95 of the effective depth, but since we calculate this is much smaller. This is what we use for the lever arm. for Z. Okay. Plus the same quantity of steel we put on the top. So this way we find a way of balancing the section of the concrete, and it can resist. Okay, so replacing the Z, 0.82 multiplied by D, that is the 450, give us this lever arm, 369 millimeters. So the main reinforcement on the bottom, the positive, replacing all the K limit, 0.167 multiplied by FCK. We are using concrete of C30, so it's 30, multiplied by B, 250 multiplied by D, that is the effective depth, 450, over 0.87 FYK, that is S500 of steel, multiplied by the lever arm that we calculated, plus the steel we got from the top of the beam, that was this one. So all this together give us 2162 square millimeters. So we could use 3 bars of diameter 32. It gave us 2412, so we are safe. It's a little more. We could put here like diameter, we even adopt this diameter on the beginning, as you can see, to get to the D, effective depth. And so that's why in the beginning we went to this one. If we put here diameter of 25, we will get 1472. So even if we increase for 1900, 5, 2454, we could go for this diameter. So if in the market there is no diameter of 32, we could go to the diameter of 25. So okay, let's go back to the 32 because we already calculate the effective depth as that. 32, 2412, just a little than before, so it's okay, it's bigger than this. So now we have the main reinforcement here on the bottom, a mid-span, and at mid-span the top reinforcement to diameter of 20. Okay, so this is a simply supported beam. We need to place some reinforcement near the support too, on the top, so it doesn't crack. So at more or less this span, 1/3 of the span here at least, so it will give us, and the minimum, what we could do, so the reinforcement there on the top will be given by this expression. The maximum between, it will be the maximum value between the minimum area of section that we calculated, 169, and 15% of the main reinforcement on the bottom here. So even if we put there, so let's see, 150, that is 50% of the main reinforcement that we put here on the bottom. We were using this one, so this no, let's put it, this gives us 324 that we calculated. So this is why for the steel on support we are using this value, 324 square millimeter, because it's bigger than the other one, 169, from this expression. So for this we can use 2 diameters of 20, give us 628. We are fine like that. So I use the 20. Why? Just because I want to save probably some money. If we have to link here another bar different from this side, we'll spend some reinforcement here extra, but if we continue just the bar, probably we will be saving on the attachment when we attach this side with this side with the steel. We can see that if we use diameter smaller, 16, 402, still it's okay. But since and usually that's what you see in the construction, you don't see someone giving you just this small, you can see, and then put here a different, no. What you normally see, it's extending what is already here on the rebar to the supports. So if it was like here 4 diameters of 20, they will extend probably 2 here. And what is giving us 2 of 20 here. We extend it, and in this case probably we spend less steel since we don't have to do this attachment this side with this one. Okay, moving on, we have so 2 rebars of 20 on one side and on another on the top on the support. And we know here the reinforcement on the bottom here is just 50% close to the support on the bottom. We'll just need 50% of this. Okay, we have the rebars, longitudinal rebars for the beam. Let's go to see first if it needs stirrups, links. And for that we start by the shear. And we have to check this to ultimate limit state according to the Eurocode. So is given this simply supported beam by this expression. It will be this shear, the factor load multiplied by the span over 2. When we take this factor load, that is 112, multiplied by the span, that is 5 meters, over 2, we get 281 kilonewtons. Okay. So in the Eurocode we have this equation, this expression here that says this shear that we calculated has to be smaller or equal to the resistance shear VRDC, and this has to be bigger or equal to the shear minimum that is given by 0.035 K3 over 2 multiplied by square root of FCK plus K1 of multiplied by press stressing. We don't have axial force here or press stressing, so it's 0 here on these corners of the expressions. So when we go for the VRD, we have the CRD that is equal to this 0.18 over safety factor of concrete, that is 1.5. What give us will be 0.18 divided by 1.5 give us 0.12. For K, the K is given by this other expression on the Eurocode, K equal to 1 plus square root of 200 over the effective depth D in millimeters. When we replace this D of 450 that we are considering, we get the K, and the K given is 1.6, that is less or equal to 2, so we can adopt 1.6. If it was bigger, we have to restringe it to 2. So now we calculate the rho that is after this equation. This rho is basically the longitudinal steel we are using close to the supports, because we are seeing first the stirrups we need on the supports, and close to the supports it's 50% of that steel, and it will be that section of area of steel divided by B multiplied by D, and that it is and we consider 50%, so it's the value we have here for the main reinforcement on the bottom divided by 2, because it's only 50% that we use here. We could use 100%, but we will be spending still that we don't need. So here we can reduce it at least 50%. We could reduce 40%, but since we don't want to scalonate and detailing a lot of steel, we go for 50% and we'll get the correct value immediately. So this is that quantity. $2,412.74 divided by 2 over B, that is 250, multiplied by the effective depth, that is 450 of the beam, what gives us 0.010, that is less than 0.02, so we can adopt this rule. So the VRD, we have all the values, we don't have axial force or press stressing, we replace all those values there and we get 71 kilonewtons. Now we have in this expression the other side, it is the minimum shear here, so it's basically, and we have all that we need, 0.035 multiplied by K, that is 1.6, multiplied by FCK of the concrete that we are using C30. The other K1 is 0.15, but we don't have per stress, it becomes 0. So multiplied by B, that is 250, multiplied by the effective depth again, that is 450, will give us a minimum shear of 46. So in this expression we have to choose the maximum value in between these two, the V minimum and the VRDC, and it will be 71.56. And since the shear that we calculate 281 is bigger than 71, it means we'll need stirrups. We need shear reinforcement. So this from Eurocode 2 for members not requiring shear reinforcement, it will mean that in this case we need shear reinforcement. And for this shear reinforcement, we can see here near the support, we're gonna do it from a distance of D, from the face of the support to there, a distance of D, the effective depth. And we have this theta. In the Eurocode, they found a condition to put the cutoff theta between 1 and 2.5 to get this verification. That is basically between the angle of theta of 45 and 22 degrees to get the VED minimum, and close to the support here will be the VED maximum. So we have here for this VED minimum the distance of D plus half of distance of the width of the support. So this VED minimum is given by this equation, that is the shear that we calculated, 281 less that distance, half of the support that is we are adopting here for this brick wall at 300 on the bottom, 300 millimeters divided by 2 plus D of the effective depth, that is 450. So that's the distance from the face of support we are considering. Multiplied by the factor load, the UDL at ultimate limit state, and this factor load it's basically 112.79. So we replace all this and we get the VED minimum, that was 214.30. We got this value here. Okay, from this value we have in the Eurocode to this other simplified equation for shear that says the shear minimum will be 0.50 multiplied by V multiplied by the root of FCK. So FCK is 30, the V is 250, the V 450. We replace everything. We get 92 kilonewtons. And since this VED minimum is bigger than this one, we can start calculating the VED maximum that goes to the support, and it basically what I told, it's the shear less half of distance from the support multiplied by the factor load. So this distance from here, half on this side to the face of the support multiplied by this top factor load. We know it's 112, we calculated. So when we replace the VED, it was 281.975 less B of support that we are adopting 300 divided by 2 by the factor load that was 112.79. He gave us 265. So in the face of the support. Okay, we can know from here even the angle. Now we have this, we could know the angle is given by this equation. The cota of theta is bigger than 1, so we are safe. We have this board, we have this graphic on the Eurocode that if we compare with the British code BS 8110. So in the Eurocode they closed this cracking that we see, the angle of the cracking with theta. They close it between the angle of cota of theta equal to 1, that is the theta of 45 degrees here on top. On the bottom they limited to 22 degrees theta, that is equal to 2.5. So it can't be less than 1 cota of theta, and it shouldn't be less than cota of theta 25. It is 22. So what happens here? It gives us, if we replace all these values on this expression on degrees, you have 70 degrees. What is less than the 22 that we are limited by the Eurocode? So the theta should be between this value. So we have to adopt theta equal to 22. We're gonna go with the links, the stirrups, pull it up to 22. So cota of theta of this, it's 3.10 and the limit is 2.5. So we adopt cota of theta equal to 2.5. Theta it's 22 degrees. With this we're gonna calculate it. So the links we have this. So we go for this equation first, the VRD maximum, that from the Eurocode we can get for this expression B multiplied by Z, that is the lever arm, and after this, so now we consider the lever arm according to the Eurocode Z equal to 0.9 multiplied by D, the effective depth, that gives us 405 millimeters. After this situation is the Z that we consider, and it will be so equal to this, B multiplied by Z multiplied by V multiplied by FCD over cot of theta plus tangent of theta in 22 degrees, that is the limit we adopt. So the V will be equal to this 0.6 multiplied by 1 less FCK, that is the concrete resistance of 30, over 250 give us 0.528. Okay, and the FCD we're gonna use from this equation. 0.85 multiplied FCK, that is 30, and the safety factor of concrete we are using 1.5 gives us 70 megapascal. So replacing everything here on this equation, we get the VRD maximum. B is 250. Z is the 405 millimeters. The V it's 0.528. The FCD is 17. So divided by cot of 22 plus tangent of 22. In rad will give us 315. So now we can compare the VED minimum with the VRD maximum, and the VED minimum it's less than the VRD maximum. What does this mean? It means that the strength of the concrete is sufficient with these links that we adopt. We are using links of 8 millimeters. So okay. After this we can go to check. So near the supports, the spacing for these links, and it's given by this equation in the Eurocode. VAD minimum equal to the area of the section of the steel over the spacing multiplied by FYD multiplied by the Z lever arm multiplied by cot of theta. So we get the spacing for one side, and it will be basically the area of steel will be 2 times, because it's stirrups where we are using 2 legs for the stirrups, and for 8 millimeters it's 50.26 square millimeters. Okay, so 2 multiplied by the 50 square millimeters multiplied by FYD that we know here on the top. FYD is divided by the safety factor of 1.15. They give us 434.78. Multiplied by Z, that is this new Z, equal to 0.9 multiplied by D, 405 millimeters. Cot of theta, we adopt the 22 degrees. What gives us cot of theta is 2.5 multiplied by 2.5 divided by the VED, this VED minimum that we got. It was 214.30. Okay, this all gives 207 millimeters spacing for stirrups of 8. So we know from Eurocode there that they limit the spacing of the links to 0.75 of the effective depth and to 600 millimeters. So even when we calculate this to be different from the previous video where we adopted a diameter of 12 and we were spending too much still because it was given us bigger spacing. So it's limited by this, and I advise to keep it on this link between 100 millimeters and 300 millimeters, the links. That's what you usually will see on the construction site. Bigger construction structures, you may get this bigger length. Okay, so we can adopt the diameter 2 legs of diameter of 8 spaced by 20. It will be okay with this 207 spaced by 20 centimeters. It is 200. Okay, now we have, so it will be links of 8 millimeters spaced by 20 centimeters, one corner of support and the other one. And now at midspan, the links that we are gonna adopt, it will be with the maximum spacing of 0.75 D. So when we get this, it gives us 0.75 multiplied by the effective depth, that was 450. It gave us 337 millimeters according to the Eurocode. Okay, the stirrups, they are vertical, so this is why. Quota of 19 it gives equal to 0, it will be this value. Okay, so we have this equation for the minimum ratio of steel. It has to be less or equal to 0.08 root of fck over fyk. When we pass the spacing to the other side, we get this equation. It will be the area of steel, that is 2 times the diameter of 50.26 divided by 0.08 multiplied by b, that is 250 square root of fck, that is concrete strength of 30 that we are using, divided by fyk, that is the steel S 500 divided by 500. Replacing all this, we get for the minimum spacing 459 millimeters. But we have to use the maximum that is allowed to us, is use this one, 0.75 of D on the midspan. So it will be give us 337. We could adopt, so 2 legs of diameter of 8 spaced by 30 cm. It means 300 millimeters, because this is the limit. Okay, so links of 8 spaced by 30 centimeters. And reaching this point, we have all the main reinforcement on the beam and the links. Now what we can do, we can define the distance that we apply the links on this side. We will call x1, the other side is the same distance, x1, and the distance here for this other beam spaced by 30, we will call it x3. So we start by calculating here these ratios. That is the, on the support it will be 2 legs of the area of 8, that is 50.26 over the spacing of 200 will give us 0.503. Okay, on the middle it's exactly the same, so we know it's 2 legs of the area of 8, 50.26, so we multiply 2 by 50 over the spacing. We are using 300, what gives us this 0.335 millimeters. Okay, square millimeters on top, meters on the bottom, so square millimeters on the bottom will give us this ratio. Okay, the other side is the same ratio than here, still middle is different. So after this, we know from the equation the VRD minimum will be equal to this. So this VRD minimum, it's basically the area over the spacing multiplied by FYD multiplied by the lever arm that was 0.9 multiplier of D multiplied by cut of theta, that is 2.5 that we adopt. Replacing all, it's 0.335 multiplied by FYD, that is still 500 over safety factor 1.15 multiplied by Z, that was 405 millimeters we calculated here, and multiplied by cut of theta of 22 degrees, that is 2.5, give us 147 kilonewtons. So now we have the VRD minimum here, and we know the VED minimum from before. Okay, at the face of the support, the VED maximum will be 265 that we calculated there at the face of the support here. And here we got 100 for the VRD minimum, 147 from here, and the UDL or factor load, it's 112 that we know from the beginning. Factor load. Okay, now we are in condition to make a triangle and get the values of x1 and x2, and it will be x1 equal to VED maximum less the VRD minimum over the factor load 112. Replacing all values, we get 1.042 meters. The x2 is basically the length of the span less b of support, because it's half of support in this side, half of that one will give us the width of the support, less 2 times x1 that we calculated, because it's less this one and less this one. We'll get the x2. Replacing all values that we have is basically L, that is the span. We are using a span of 5 meters, less so b of support, that was 300 millimeters, so less 2 times, we can put meters, so we calculate everything in meters, less 2 times x1, that is 2 multiplied by 1.042 will give us 2.616 meters. So x2 will be 2 meters 61 and x1 1.042. And we have now the distance for the links on this side where we're gonna put them, and the distance for these links on the middle. So we have calculated everything. We can make a resume here in AutoCAD. We have the main reinforcement here on the bottom. That was 3 diameter of 32. You can see it here on the table that we calculated before. On the bottom, the main reinforcement 3. We could call it in English H32, but 3 diameter of 32, and the distance on this other 50%, it will be 50% only of this 3 diameter of 32 here on the bottom. For me, we don't need more than 50%, one side and the other one close to the supports. Here on the top, the area of sectional steel that we calculated was 2 diameters of 20 on the top, 2 diameters of 20 here. Okay, and close to the supports we need reinforcement that was given. We adopted the to extend this 2 diameter of 20. We could have reduced it, but I think we'll save more steel like that instead of using other diameter. So for the support here we adopted this one, so we just extend 2 rebars of 20. So we have all the longitudinal steel on bottom and top, on supports, on the corners and midspan, and the links, these stirrups that we calculated here, that are on this corner at a distance of 1 meter of spaced by 20, so diameter of 80 millimeters spaced by 200 millimeters on the corner here, x1, diameter of 8 spaced by 20, and in the middle was links of diameter of 8 spaced by 30 in x2 distance. Here, diameter of 8 spaced by 300 millimeters on x2. So we finished this calculation, and it looks like a good beam. With we see this kind of beam normally a lot on the construction sites where the steel is saved. Here is 50% of the main reinforcement. We can put that 0.50 of the span here on one side and the other one, this length too, this distance, and it will be okay.